Okay, welcome to Principles of Electric Circuits. This is chapter 11. This is AC/DC, not just the band, but it's a breakthrough. So, welcome back to, again, if this is going to be a podcast, Magnetic Minds, the podcast that wires your thinking straight into the core of electronics. Again, my name is Professor Vasquez, and today we're flipping the switch literally. We're entering, again, chapter 11 of your textbook, Principles of Electric Circuits, Conventional Current, and the topic is foundational to nearly everything that powers your world. So, introduction to alternating current and voltage. So, in the last chapter, we explored magnetism, its electrifying influence on motion in machines. Now we take this next step into the world of alternating current, or AC. Right? AC isn't just an alternative to direct current, it's the dominant form of electrical energy transmission worldwide. From your home outlets to power stations, it's AC that keeps the lights on. Not AC as an air conditioning, AC as an alternating current. Right? So what we're going to cover is what makes AC different from DC, how voltage and current alternate in waveform, and the importance of frequency, period, and amplitude, and how all this ties into the sine waves that pulse through your devices every second of every day. So grab your waveform charts and get ready to oscillate. We're diving into the pulse of the power grid. Okay, so this is where the shape of power meets the sine wave. So now that we've entered the world of alternating current, we need to understand the waveform that defines it, and we call that the sine wave. The sine wave isn't just a neat curve, it's the fundamental shape of alternating voltage and alternating current in most electrical systems. And why? Because it's smooth, continuous, and mathematically predictable. It rises to a positive maximum, falls through zero through a negative maximum, and then returns back to zero over and over and over and over again. And this repeating cycle makes it perfect for delivering power efficiently. So if we look at the diagram here, you're going to notice that the vertical axis represents voltage or current, and the horizontal axis is time. And what about those peaks? Those are the maximum values, positive and negative. That up and down motion represent the change in polarity and direction. So unlike DC, which stays constant, AC flips back and forth. And this oscillation is what allows transformers and AC grids to work so effectively. So when you flip on a light switch or charge your laptop, you're not just using electricity. You're tapping into a perfectly timed electrical rhythm that's dancing to the tune of a sine wave. I'm so tempted to talk to you about Tesla, Nikola Tesla, and Edison, but I'm going to leave that to you to investigate on your own. Okay, let's talk about waves you can't see but can always count on. So let's take a step back from the waveform chart and take a moment and just reflect on something like what we see here on the image, the ocean. So just like the waves on water, electrical waves, they're disturbances. They move energy through a medium, and the big difference, we can see ocean waves, but electrical waves are invisible to us. Still, they follow the same rhythmic principles. They rise and fall, they repeat over time, and they carry energy with every cycle. And here's the most important takeaway from this slide. It has nothing to do with going to the beach or not going to the beach. It has to do with all periodic waves can be built from sine waves. For example, square waves, triangle waves, even complex audio signals, they're all made by stacking sine waves of different frequencies and amplitudes. And this makes sine waves the foundation of all waveforms in electrical engineering. So even though you can't see them with your eyes, sine waves are everywhere. In your power lines, your phone signals, your music. In a way, sine waves are the alphabet of electronics. So you learn the shape and you can start reading the language of circuits and systems. And just a very interesting aside, if you look at the properties of sine waves, you can also relate that to the fluctuations in other systems like social interactions with people in societies, how things go up and down. So the principles here aren't just related to electrical engineering or the phenomena we see in nature. These principles apply in fields you wouldn't have guessed. All right, continuing with two key ingredients, the amplitude and the period. So let's zoom in on what makes a sine wave tick. Every sine wave has two essential characteristics that define its shape and behavior, which is the amplitude and period. Amplitude, represented by A, is the maximum value the voltage or the current reaches. And we measure that from 0. Think of it as the height of the wave. So in this example, the amplitude is 20 volts, which means the wave oscillates from plus 20 volts to negative 20 volts. And the energy in the signal, well, it lives in this height. Right? The period, it's represented by the symbol T or the letter T. And it's the time it takes to complete one full cycle of the wave. So it's the length of one full trip from 0 to peak to trough and back again. Here the period is 50 microseconds. These two values help define how strong the signal is, which is the amplitude, and how fast it's cycling, which is the period. And together they shape everything from audio tones to power signals. So if amplitude is the wave's muscle, the period is its tempo. And we'll soon see how that leads directly into frequency. Measuring the beat, amplitude and period in action. So we've defined amplitude and period, and now it's time to see how they play out across a full waveform. On this slide, we can observe two main ideas. First, the period, right, denoted by T, capital T, of a sine wave that can be measured between any two matching points on the waveform. And that could be peak to peak, zero crossing to zero crossing, or any repeating spot as long as it defines a full cycle. The period tells us how long one wave cycle takes. And then second is amplitude. It's not measured from the bottom to the top of the wave. That's total swing. So instead, amplitude is the distance from the center line, which is we call the mean value, to the maximum of the wave. That's the strength or intensity of the wave's reach in either direction. So think of it this way. Period gives us a rhythm, how often a wave repeats. Amplitude gives us a volume, how intense each pulse is. And together they define the waveform's behavior, whether you're powering a motor, transmitting a signal, or you're producing some audio. All right, frequency, the speed of the wave beat. So far we've covered amplitude and period. And now it's time to talk about the pulse that powers our electric world, so frequency. Frequency, symbolized here by the letter F, or the symbol F, is the number of complete cycles a wave completes in 1 second. Right? So it's measured in hertz, capital H, little z is the symbol, and it's named in honor of Heinrich Hertz, which for some reason always reminds, well, I know why, it reminds me of ketchup, like Heinz. Anyway, the physicist who first proved electromagnetic waves exists. That's who that was. So before that, we just called it cycles per second. So let's look at the example here on the slide. You'll see 3 full sine wave cycles fit into 1 second, and that means that the frequency is 3 hertz. So F would be equal to 3 hertz, H sub z, H little z, right? And that seems simple, right? More cycles in the same time means that the frequency goes up, so you have higher frequency. Fewer cycles within the same time means you have lower frequency. So this concept is vital because frequency defines the pitch of a sound wave, the channel of a radio station, the power grid standard. So in the US, it's 60 hertz, while in Europe, it's 50 hertz. And there's a direct relationship between frequency and period, where frequency is equal to 1 over the period. So F is equal to 1 over T. So if you know how long one cycle takes, you know how many fit into a second, and vice versa. Frequency isn't just how fast something repeats, it's how consistently we can count on it to do so. And that's why it's foundational to every form of electrical timing and transmission. All right, two sides of the same wave, right? The period and frequency. So now that you know what period and frequency mean, let's make one thing clear. They're not just related, they're mathematical opposites. That's right, you heard it from me first. Period and frequency are reciprocals of each other. So F is equal to 1 over T, or frequency is equal to 1 over T, the period. And vice versa, T is equal to 1 over F, or period is equal to 1 over frequency. So if you know how long one wave takes, the period, you can figure out how many happen in a second, which is the frequency, and vice versa. It's a simple flip. Just hit that 1 over x key on your calculator. So here's an example. Let's say the period is 50 microseconds. And to find the frequency, again, I'm going to say plug and chug for my old math teacher, meaning just plug in the numbers and get the answer. F is equal to 1 divided by 50 microseconds. And again, don't forget the micro, 10 to the negative 6. That's going to equal 20,000 hertz or 20 kilohertz. So that means 20,000 full cycles are happening every second. And this conversion is especially helpful when you're working with signals in audio, radio, or digital timing. So where things are often measured in microseconds or megahertz. So the thing to remember here is shorter period, higher frequency, longer period, lower frequency. And it's that seesaw of time and repetition. So if you master this, and you've unlocked one of the most common rhythm tools in all of electronics. All right, let's continue where waves begin. Right, so we're going to turn motion into voltage. So we've talked about what sine waves look like and how we measure them. Now let's explore how they're actually created, starting with the heart of it all, an AC generator. Right, so here's the basic principle. When a conductor, like a wire loop or a coil, rotates inside a constant magnetic field, it cuts across the magnetic lines of flux, and this motion causes voltage to be induced. And the shape of that voltage is a sine wave. So the slide here shows the conductor turning inside a magnetic field between north and south pole. At point A, the conductor is moving parallel to the magnetic lines, and that's and what's the result of that, right? So we have no voltage since it's parallel. So no voltage is induced because there's no cutting action. And the key point just to this one slide into this one moment in time here is that you have no relative motion across the field line. So that equals no induced voltage. And this setup where rotation creates variations in flux, this forms the basis of how generators and power plants, wind turbines, and alternators work. Alternators just like the one in your car. So even though you can't see it, every outlet in your home delivers power that's been generated by this exact motion, turning mechanical energy into electrical sine waves. Now, when you're cutting the field, that's where you see the voltage peaks. So in the last segment, our conductor began its rotation, but no voltage was induced at point A because it was moving parallel to the magnetic field lines. Now we've reached point B, and here's where things get exciting. I hope it's exciting for you, because it's exciting for me. So at this point, the conductor is moving perpendicular to the magnetic flux lines. And that's the key. Maximum voltage is induced when motion is perpendicular to the field. Why? Because now the conductor is cutting through the magnetic field lines at full speed and full angle, generating the most change in flux per second. So on the sine wave to the right, point B corresponds to the positive peak, the highest point in the cycle. And this is where electromagnetic induction is at its strongest. And this is the physics behind our power grid, our car alternators, and in portable generators. So as the coil rotates past this point, the output voltage reaches its maximum, then begins to decrease again as that angle shifts. And what we're watching is the sine wave take shape in real time. It's driven by rotation and the geometry of the field. Okay, let's look at the wave as it crosses zero, the midpoint of the cycle. So again, we're halfway through our rotation and our conductor has reached point C, the very top of the circular path. So what happens here? Well, just like at point A, the motion of the conductor is once again parallel to the magnetic field lines. That means it's not cutting across them, and therefore no voltage is induced. On the sine wave, point C corresponds to the zero crossing, where the voltage falls back to zero after reaching its positive peak. And this is a turning point in the cycle. The voltage is no longer increasing. The direction of the induced voltage is about to reverse. And you're saying, why? Because from here on, the conductor begins moving back down, changing the direction in which it cuts through the magnetic field. That's what makes AC truly alternating. Both the magnitude and direction of the voltage change in a smooth, predictable rhythm. And so what you're witnessing is the symmetry of the sine wave in motion. Each quarter turn marks a key change in the waveform's direction and strength. Okay, let's move into the polarity when it's reversed, or the negative peak. So our conductor has now rotated to point D. And this is where things get really, really interesting, right? So I threw in an extra really, so hopefully that will increase your interest in making it interesting. Because it mirrors point B, but with a critical twist. So at point D, what's happening? The conductor is once again moving perpendicular to the magnetic field lines, but now it's traveling in the opposite direction. So this reversal in motion causes the induced voltage to flip polarity, and it generates a maximum negative voltage. On the sine wave, this is shown as a negative peak, the lowest point of the wave, directly opposite of the positive peak we saw earlier at point B. And this shift is what makes alternating current alternate, right? The voltage doesn't just rise and fall, it reverses direction entirely. The electrons begin pushing the other way, back and forth through the circuit, completing the cycle. I've never been in a mosh pit. I know they go back and forth all the time. Something like that, maybe. I may be wrong. I don't know what they do in a mosh pit. You know what? Probably not, because I see them jumping up and down, and maybe it is more representative of what you see in a mosh pit than we know. Sorry, let's keep going back to the lecture. So maximum field interaction occurs here. You have full polarity reversal and the symmetry that defines sinusoidal AC. So it's motion turned into electricity and motion turned around to reverse electricity just by rotating a wire in a field. So we end up back where we began, one full complete cycle. We've now arrived at the final frame of the rotation. The conductor returns to its original orientation, parallel to the magnetic field lines, just like at point A and point C. Right? There is no voltage induced at this moment because there's no cutting motion across the field lines. This brings us full cycle, or full circle, literally. We've now completed one full cycle of sine wave generation. So let's go ahead and break that down. We started with 0 voltage at point A, reached a positive maximum at point B, dropped back to 0 at point C, dipped into a negative maximum at point D, and returned to 0 here at the end of the rotation. And that's a complete sine wave. That's the smooth, continuous rise and fall, which is the hallmark of all alternating current produced by mechanical motion in a magnetic field. The principal powers, your local utility grid, alternators in cars, wind turbines, again, emergency backup generators, which we use quite a bit in hospitals. So even though the slide shows a simple rotating wire, its basic motion is the heartbeat of modern energy. I try to link that there to medical. Okay, just so make sure you understand, I'm not reading the slides for you. You can go ahead and read that on your own. I'm just going to go ahead and give you a nice description to summarize the whole thing. All right, so here we're talking about the alternator, turning spin into sine. Again, you understand how a sine wave is created. Let's look at a real-world device that does exactly that, which is the AC generator. It's also called the alternator, again, just like your alternator in your automobile. So at its core, a generator is a rotational to electrical converter. So it transforms mechanical energy like a spinning shaft into an alternating current. And that's how it works. A magnetic field is held stationary. A rotating armature, which is a loop or a coil of wire, spins inside the field. As it cuts through the magnetic lines of flux, an AC voltage is induced in the coil, just like we saw in the earlier slides. But now we go further. That voltage needs to be transferred to an external load, like your light bulbs or outlet, the grid. And that's where slip rings and brushes come in. So slip rings rotate with the armature. Brushes stay stationary, maintaining an electrical contact with the rotating slip rings. And it's a clever setup that allows generated AC voltage to flow continuously to the load without tangling any wires. Um, Smaller alternators might use permanent magnets like the one shown here. Larger systems like those in power plants, they often use field coils to generate stronger magnetic fields. Either way, the principle stays the same. Spin a conductor in a field, you get AC power. Right, let's go ahead and increase the complexity of this just a little bit. Let's add more poles, right? More power, frequency by design, right? So in the last segment or the last slide, we saw how a basic AC generator produces a sine wave by rotating a conductor within a magnetic field. Now let's take that concept up a notch. I feel like Emerald. Let's kick it up a notch. I forgot what he says already. Bam! Literally. And here's the key idea for that. The more magnetic poles the generator has, the more cycles it produces per revolution. So let's say you've got a 4-pole generator, and that means 2 north poles and 2 south poles arranged around the rotor. That's not a very good a generator, but still, just we're increasing the complexity. So as the coil rotates through each of these field pairs, it generates 2 complete cycles, right, of voltage per revolution instead of just 1. So let's take a look at this diagram. You have 1 full mechanical revolution of the coil. That results in 2 full sine wave cycles on the voltage output. And that's because every time the conductor moves from one pole pair to the next, it completes half a cycle, and double the poles, double the cycles. And this is how, again, how power plants can fine-tune their output frequency. So for example, again, in the US, where we use that 60 Hertz AC for power generation, the generator speed and number of poles are carefully selected so the output waveform repeats 60 times per second. More poles means you can generate higher frequency without spinning faster. A huge advantage for large machinery. So it's not only that it's a smooth sine wave, it's also scalable. So let's talk about function generators. If you're in your lab, go ahead and take a look at the function generator that's on your workbench. We've explored how AC is generated in the real world, from spinning conductors and magnetic fields, but in the lab, we have a much more compact and flexible solution for waveform creation, and that's the function generator. Think of this like the Swiss Army knife of signal creation. It lets you produce a variety of electrical waveforms at different frequencies and amplitudes at the push of a button. So let's go ahead and walk through some of the features of a function generator. Again, if you're in your lab, just follow along and try to find these functions within the actual device you have. If you're not, just follow along here on the image of the function generator we have here on the slide. So function selection lets you choose your waveform type. So you'll have sine wave, square wave, triangle wave, right? Sine wave, we know what that is, a smooth natural wave. Square, that's a fast switching, that's great for digital circuits. And a triangle, that's an interesting way of saying triangle. Now I want to say it like that, a triangle, okay, I think I want to say it like that now. That's a linear rise and fall. It's useful in testing linear responses. You also have frequency controls, and they come in 2 parts. A range, which sets the base scale. So for example, you might have hertz, kilohertz, megahertz, and so forth. And an adjust, which fine-tunes the exact frequency. You also have an output level, which is the amplitude, and that determines how tall the waveform is again, how much voltage it swings above and below the baseline. You can control the DC offset. This shifts the entire waveform up or down relative to ground. That's useful when testing circuits that don't center around 0 volts. For the most part, we're going to be doing everything centering around 0 volts, but not all signals fluctuate above and below 0 volts. We can look at the control the duty cycle, and that's important when generating square or pulse waves. That lets you control how long the signal stays high versus low. And of course, there's the readout showing your frequency or your voltage settings. The multiple outputs for connecting to oscilloscopes, amplifiers, or circuit inputs. So in short, your function generator that you have in your lab, they may look different from what you have here in the picture, but they all have the same thing. They don't just simulate waveforms. It lets you build and manipulate them in real time. It's essential in labs for testing amplifiers, timing circuits, filters, and more. So if you're learning electronics, this is the sandbox where waves come to life. All right, so beyond the basic waves, right, we have arbitrary function generators. So if a function generator is your waveform workbench, then something like an arbitrary function generator or an AFG, that's your digital waveform uh, generator, right? So an AFG offers much more flexibility and power than the traditional sine, square, triangle wave generator. The model that you see here, the Tektronix AFG 1022, it's a perfect example. It comes loaded with 50 built-in waveforms, multiple output models like repetitive, burst, and modulated signals. It has two-channel capability for synchronized or independent signal generation. And this means that you can go far beyond textbook signals. So you want a half sine burst, a custom modulated RF tone, or a biomedical pulse pattern. This AFG makes that possible without external programming. And you can take it a step further. The AWG, the arbitrary waveform generator, it pushes things a little further. It allows you to draw, upload, or mathematically define your own complex signals. Exactly how you want them. And why does this matter? So in modern electronics, you're not always dealing with clean sine waves. You need to test noisy data streams, mixed signal systems, power ripple under switching loads, communication bursts and packets. And that's where the arbitrary function generator shines. That means you define the waveform, not just choose from a list. So from classroom labs to advanced research, AFGs and AWGs let you simulate the real world signals that circuits must handle. Some of you actually have AFGs in your lab. Some of you have the traditional function generators. Let's talk about peak performance, measuring sine wave voltage. Right? So let's turn our attention to the numbers that define sine wave behavior, starting with the peak value. So in AC systems, and I'm going to have to stress this, alternating current systems, so you don't get confused with air conditioning, right? So in AC systems, you don't just care about the shape of the wave, you care about how strong it is. And that starts with the amplitude, which is, in electrical terms, it's often called the peak value. And that's abbreviated V sub P for voltage or voltage peak. All right, this is the maximum voltage a sine wave reaches above the zero line. In the waveform shown here, you can see that the wave rises to plus 20 volts. It falls down to negative 20 volts. So that makes the peak value V sub P exactly 20 volts. Right? This is not to be confused with peak-to-peak voltage, which we'll get into in a later slide. V sub P only looks at the height from the center line, or the 0 volts, to the top of one of the peaks, either the top of the positive or the top of the negative peak. And this value is critical when you want to specify component ratings, comparing signal strings, you're calculating measurements like RMS voltage and average voltage. So when you see V sub P is equal to 20 volts, think of this. This is how far the wave stretches upward from zero and how much energy it can deliver at its maximum. Okay, let's go one step further or beyond the peak, right? So we have peak-to-peak voltage and RMS voltage. RMS just stands for root mean squared voltage. And peak-to-peak, I kind of described it before. If we talked about V sub P, which is the peak voltage, but a sine wave has more than one way to describe its strength, right? We look at it, we can describe it a different way. We can say peak-to-peak voltage, and this is a total swing of the waveform from its maximum positive value to its maximum negative value. So voltage sub PP, a little PP, that means voltage peak to peak. And that'll be 2 times whatever the voltage peak is. So an example shown here, the waveform peaks at plus 20 volts and dips at negative 20 volts. So the voltage peak to peak is 40 volts, 20 volts up and 20 volts down. This is useful when you're visualizing the entire range of a waveform that is occupied on a scope or an input terminal. When we say RMS voltage, root mean squared voltage, this is a kind of average, but not a simple one. It tells you the equivalent DC voltage that would deliver the same amount of power. So V sub RMS is going to be equal to 0.707 times whatever that voltage peak value is. So in this case, for our 20 volts peak, 20 V sub P, the RMS equivalent would be 14.1 volts. And this is the value most meters display when measuring AC voltage. And it's the one used in power calculation. So if we want to recap from this slide, V sub P is equal to 20 volts. V sub PP, V sub peak to peak, is going to be 40 volts. Remember, going 20 volts up, 20 volts down. And V sub RMS, the root mean squared, is going to be 14.1 volts. Each gives a different perspective of the waveform's behavior and its effect. Let's go ahead and continue with the average. So what the wave feels like over time. So we've covered peak to peak, and we've covered RMS values. So let's look at a lesser known but still useful measurement, which is the average value of the sine wave. But there's a little twist. When we say average, we really mean the average of just the positive half of the cycle, also known as the half wave average. That's because over a full cycle, a pure sine wave averages out to 0. You have positive, negative halves, and each of them cancel out. So when engineers refer to the average, they typically mean the average value above the 0 line. So by definition, the average value of a sine wave is V sub average is equal to 0.637 times voltage peak. In the example shown with a peak voltage of 20 volts, plugging the numbers in, the average becomes V sub average is equal to 0.637 times 20 volts, and that ends up being 12.7 volts. This number is useful for things like rectified signals, like in power amplifiers after a diode, analog meter readings, so when designing filters that respond to signal averages rather than RMS power. And just keep in mind that V sub P gives you maximum voltage, V sub RMS gives you the heating electrical power equivalence, and V sub average gives you a measure of the effective swing in just the positive direction. So measuring the spin, this is where degrees and radians and sine waves come into play. So if you truly want to understand the sine waves, especially in AC systems, we need to think not just in time, but in angle. You're asking why? Well, because every sine wave is based on rotation, whether it's a conductor spinning in a magnetic field or it's a mathematical circle traced over time. So how do we measure the rotation in degrees or radians? Let's break this down. One full circle is 360 degrees. I'm sure we know this. That same circle equals 2 pi radians. So a radian is defined as the angle where the arc length equals the radius of the circle. So on the diagram, you can see 1 radian marked out with a curved arc that's equal in length to the radius. And why this is important? Because when we analyze sine waves mathematically, especially in electronics and in signal processing, we often express the waveform's position in terms of radians, not seconds. On the sine wave graph, the horizontal axis uses radians, so 0 to 2 pi equals 1 full cycle. Pi is half of that, which is 180 degrees. Pi over 2 is just a peak. 3 pi over 2 is the negative peak. So this notation helps us easily describe the wave's shape using trigonometric functions, and we end up with the formula. We can solve this for V of t, is equal to V sub p times sine theta. And this is where theta is an angle in radians tied directly to time and frequency. Okay, let's look at converting circles from degrees to radians and back. In our last segment, we introduced the idea of measuring sine wave phase in radians. Now let's do something more practical. How do you convert between degrees and radians? And the math is simple because the relationship is fixed. So we said 360 degrees is equal to 2 pi radians. So that means we can convert between the two using a proportional relationship. So to convert degrees to radians, radians is equal to 2 pi divided by 360 degrees times the degree you're trying to convert. And if you're wanting to simplify that, radians can also be equal to pi over 180 times the degree you're trying to convert. All I did from there is just reduce 2 pi over 360 to pi over 180. It's the same proportion. Now an example would be 90 degrees. We want to convert that to radians. So radians would equal to pi divided by 180 times that 90 degrees, and we end up with pi over 2 radians. Now, if I want to convert radians to degrees, right, degrees would be equal to 360 degrees divided by 2 pi times the radians you're trying to convert. Again, we can also simplify this, where degrees is equal to 180 over pi times the radians. And I just basically did the same thing. 360 over 2 pi, I just reduced that to 180 over pi. So if we're given pi over 4 radians and I want to convert that to degrees, you just, again, plug and chug. The degrees would be equal to the formula 180 degrees divided by pi times, again, the radians we're trying to convert, which is pi over 4. And this ends up equaling 45 degrees. And these conversions, they're crucial in AC analysis. Engineers often use degrees when discussing phase shifts, like a 90-degree lag. It's okay if you don't understand what that means right now. Calculators and equations prefer radians and trigonometric functions. So keep these two conversion formulas handy, especially when switching between waveform visualization and mathematical analysis. And we'll get some practice on converting these back and forth. Okay, let's go ahead and look at calculating the wave or instantaneous voltage, right, from the wave. Now that we've defined the sine wave and the measurements that describe it, let's get a little mathematical. How do we calculate the voltage at any specific point in the sine wave? Well, we can use the sine wave equation. V is equal to V sub P times sine theta, right? V is that instantaneous voltage at a particular moment. V sub P is the peak voltage or voltage peak, however you want to say it. Theta is the angular position, either in degrees or radians. And what this tells us is at any given angle on the waveform, we can compute the voltage using the sine of that angle. Let's go look at this example. If V sub P is equal to 25 volts, and we want to know the voltage at 50 degrees, we calculate V is equal to 25 times sine 50 degrees. Plug and chug, put that into your calculator. That ends up being 19.2 volts at that moment. And if you need to convert 50 degrees to radians, just apply theta is equal to pi over 180 times that degree that you're trying to convert, right? So theta is equal to pi over 180 times 50 degrees. And you plug that in, you're going to get 0.873 radians. So whether your calculator is set to degrees or radians, oh, and by the way, make sure you know what your calculator is set to. So you may be doing and punching the numbers incorrectly, but if you have it set to the wrong thing, you're going to have the wrong answer. So in other words, I'm not going to have 0.873 degrees when I meant to say 0.873 radians, right? But doing this, you're going to have the tools to find any point on the sine wave. The formula becomes essential when you're analyzing timing, NAC circuits, phase shifts, which we're going to talk about later, and signal sampling. Let's go to work on visualizing the math, right? So plotting the instantaneous voltage. In the last slide, we used the sine wave equation to calculate the instantaneous voltage at some specific angle. So V being equal to V sub P times sine theta. And we found out that for a 25 volt peak voltage at 50 degrees or at 0.873 radians, the instantaneous voltage was 19.2 volts. And here on this slide, you'll see that the result is plotted on the sine wave. And here's what's happening in the graph. The horizontal axis is theta, the angle, and that's measured in degrees. The vertical axis is the resulting voltage, V, right? And the wave peaks at V sub P is equal to 25 volts at 90 degrees. So that's the peak. And then at 50 degrees, we drop a vertical line and see that the voltage at that point is 19.2 volts. Again, you can't be that accurate if you're doing graphical methods, so that's why mathematical methods are more important. Graphical methods will just kind of give you a visual. But this visual confirms what we calculated. The wave hasn't reached its peak yet, but it's already delivering most of its potential voltage at 50 degrees. And you can calculate and plot any point on this curve using that sine equation. So remember that this approach works for both voltage and current as long as they follow sinusoidal behavior. So in AC analysis, understanding the instantaneous value helps you to do a couple of things: predict waveform timing, model circuit responses, and calculate how current and voltage interact at specific moments. Let's move on to phase shift. I mentioned this a couple of times, right? And so timing is everything. Let's say you have two sine waves with the same frequency and amplitude, but one of them starts a little earlier or a little later than the other. And that difference is what we call a phase shift. It's one of the most critical concepts in AC analysis. The phase of a sine wave tells us where the wave is in its cycle, how far it has rotated compared to some reference. So to represent this in the sine wave equation, we modify that equation just a little bit, and the equation turns into V sub t is equal to V sub p, sorry, not V sub t, I'm sorry, V with respect to t, in other words, with respect to time. I know the slide says just v. So v is equal to v sub p times sine of theta plus or minus phi, or phi. Right? So where v is the peak voltage, theta is that angular position, phi is that phase shift in degrees or radians. So if you add phi, the wave shifts to the left and it leads. If you subtract phi, the wave shifts to the right and it lags. And this is how we mathematically describe situations like a voltage leading the current in a capacitive circuit, which we'll talk about those in a week or two, capacitive and inductive, or current lagging voltage in an inductive system. Phase shift, it's especially important when multiple sine waves interact. So in AC power systems, in signal synchronization, and in communication systems, it helps us quantify not just what is happening, but when it's happening in relation to something else. So when a wave follows the leader, we call that phase lag. Let's take a look at that concept of phase shift, and we're going to put it on a graph. So in the example we see here, we're looking at a sine wave that lags behind a reference waveform. It's like a second runner leaving the starting line just a bit late. And here's what's happening in the graph. The blue wave is the reference sine wave. The magenta wave is the lagging waveform, so it's shifted to the right. And the equation for this sine wave would be V is equal to 30 times sine of theta minus 45 degrees. That minus 45 is the phase shift. And it tells us that the wave reaches each key point 45 degrees later than the reference. So at 0, the reference wave is already climbing upward, but the lagging wave hasn't even crossed 0. It's still below the axis. That is what's called a negative negative phase shift, and that's what it looks like. A delay in wave timing is also called a lag. So this kind of shift is common in inductive circuits where current lags behind voltage, and in systems where response time or reactive energy storages affects the timing. And the key takeaway here is that a left shift will be sine of theta plus some phi, and that means it's a lead. A right shift would be theta minus phi, which ends up being a lag. And now that you can read and write those shifts directly into Wave's equation, just keep moving forward. All right, let's move to the other part of the phase shift. We're going to talk about a phase lead, when the wave gets ahead. So again, we've seen what it looks like when a sine wave lags behind a reference. Now let's flip that around. This time the wave is leading. Take a look at the graph. The blue wave is once again the reference waveform, and the magenta wave has a positive phase shift. That means it's reaching its key point sooner than the reference. So at 0 degrees, it's already above the axis, while the reference wave is just crossing 0. And the equation for this leading wave is V is equal to 30 times sine of theta plus 45 degrees. The plus 45 degrees tells us that the wave has shifted to the left. It's ahead of schedule by 45 degrees. So this type of phase shift is typically in capacitive circuits where voltage lags current, and the waveform associated with the current is said to be leading. You'll often hear this phrasing in power systems. So current leads voltage in a capacitor, voltage leads current in an inductor. Again, phase shift gives us a language to describe timing differences, which are critical when analyzing power flow, signal synchronization, or wave interaction in reactive components. And we'll talk about reactive components a little later in this course. All right, let's continue on with phasors, sine waves that spin. I have a nice animation for this, and I'll show this to you in class. This doesn't do it justice, this still image. So you've seen sine waves drawn across time, but what if I told you that sine waves can also be visualized as something rotating? And that's the concept behind phasors. A phasor is a rotating vector that traces out a sine wave as it spins around a circle at a constant rate. So think of it as an arrow spinning like a clock hand. It rotates. The vertical projection of the tip creates a sine wave you see on a graph. Again, it means so much. There's a GIF and there's a video that kind of illustrates this. It's so much better than just looking at the still image. The diagram here, though, shows a vector rotating counterclockwise. So at 0 degrees, it points to the right, which is 0 vertical projection. At 90 degrees, it points straight up. The sine wave hits its peak. At 180 degrees, it's pointing to the left, and it's at 0 again. And at 270 degrees, it's pointing down at the negative peak. So every full rotation equals 1 full cycle of the sine wave, which means the rate of rotation equals the wave's frequency. So why use phasors? Because in AC analysis, phasors give us a powerful tool to represent the sine wave compactly. I had two words in my head at the same time. They handle phase shifts visually. They simplify circuit calculations using complex numbers, and we're going to get into complex numbers, which you should have learned at the end of your algebra course. But instead of calculating voltage and currents in the time domain, we shift the phasor domain where sinusoidal behavior becomes a matter of vector addition and angle differences. Okay, so hopefully this looks a little familiar to you, the trigonometry behind the phasor, a right angle revolution. Let's take a moment to bridge two worlds, the rotating phasor and the math behind it. And that math is good old trigonometry. Trigonometry you probably covered in a pre-calc course or possibly even at the end of an algebra course. So phasors aren't just spinning arrows, right? They can be broken down into right triangles where we can use sine, cosine, and tangent to analyze them. So on this slide, you're looking at a right triangle formed by the phasor. The angle theta between the phasor and the horizontal axis, the opposite side, which represents the instantaneous value of the sine wave. The hypotenuse, which is the peak value or magnitude of the phasor. And if you remember from basic trig, you know that sine theta is equal to opposite or over hypotenuse. And at this particular moment, I'm thinking about a Key and Peele skit. I won't repeat it here, but I want to. All right, let's keep going with the slide. In phasor terms, so we have sine theta. It gives us the vertical projection, the sine wave. And if the hypotenuse is v sub p, then v is equal to v sub p times sine theta, and the same formula we've been using. So this matters because it means phasors let us apply triangle rules to AC waveforms. We can analyze AC circuits using geometry, and we can solve for voltage and current relationships without time domain complexity. This is the right triangle foundation for phasor diagrams, vector addition, and eventually impedance analysis, which I think is super important for kids in K through 12, not obviously K, but somewhere in their high school years, that they should be studying geometry and trigonometry. Continuing on with phasor angles and spinning with precision, right? So far we've talked about what a phasor is and how trigonometry helps describe its behavior. Now let's dive into how we express a phasor's position at any instant in time. So a phasor's position is all about angle, specifically how far it's rotated from a reference direction, which we usually define as 0 degrees on the right-hand horizontal axis. And there's two ways to express this angle. A positive angle, theta, measured counterclockwise from 0 degrees, the standard in engineering and circuit analysis. So for example, a phasor pointing straight up is 90 degrees. Negative angle would be theta minus 360, and this represents the same position but from a clockwise perspective. Often we use this when we're describing lagging signals. So think of it like this. If you rotate plus 90 degrees counterclockwise, it's the same as negative 270 degrees clockwise. Mathematically, they describe the same phasor angle, just using different rotational conventions. This is powerful because it allows phasors to represent phase shifts precisely. It translates rotational motion into linear waveforms. It can be graphed and compared when signals are out of phase. So when we say two phasors are 90 degrees apart, we now know what that means, that one has rotated farther than the other, and that rotational difference shows up as a waveform shift in time. Let's continue on with angular velocity, and that just says how fast the phasor spins. You've learned that a phasor is a rotating vector, and it represents a sine wave, but how fast does it rotate? That brings us to what's called angular velocity, and that's symbolized by the Greek letter omega, right? Little w, basically. When a phasor completes one full rotation, we said that's 360 degrees or 2 pi radians, and it traces out one full sine wave cycle. The rate at which this happens is called angular velocity, and it's directly tied to the frequency of the sine wave. And here's the relationship. Omega is equal to 2 pi f, right? So angular velocity is equal to 2 pi times the frequency. So W is angular velocity in radians per second. F is frequency in hertz. So again, converting frequency to angular velocity or vice versa. So if your signal is oscillating at 60 hertz, like the US standard power, then omega would be equal to 2 times pi times 60 hertz, sorry, and that's approximately 377 radians per second. What this value tells us is how quickly the phasor spins around the circle and how fast the waveform cycles in real time. Now, if the sine wave starts at time t equal to 0 and has no phase shift, we can express the instantaneous voltage at any time with this equation. So V would be equal to V sub P times sine of 2 pi ft, or 2 times pi times frequency times time. And this is the time domain equation of a pure sine wave. It wraps up amplitude, V sub P, frequency, which is F, and time, which is T. And this version is essential when modeling signals in software, or you're analyzing AC sources, or even programming oscillators in embedded systems. Writing the wave, and what that means is you have AC that's writing on a DC level. Let's wrap up this session with a concept you'll see often in both signal generation and power circuits: the superposition of AC and DC voltages. Superposition is nothing to be scared about. It just means that you're putting two signals on top of each other. And even you can put an AC and a DC signal on top of each other, or two AC signals. In many real world scenarios, a waveform doesn't just alternate symmetrically around zero. So instead, the AC signal can write on top of these DC voltages. That creates what we call a composite waveform. So in the left diagram A, the DC voltage is greater than the peak of the AC component. So V sub DC is greater than V sub P. So the entire waveform stays positive. It never crosses zero. This is useful in circuits where purely positive signal is needed, like a certain biasing or sensor circuits. On the right diagram B, the AC voltage swings both above and below the DC level. So here, V sub DC is less than V sub P, so the waveform dips below zero during part of the cycle. And what that means is that the signal reverses polarity. That's a behavior that must be accounted for in component ratings. Some components can only take certain magnitudes of voltage in opposite directions. We'll talk about those later. But in both cases, the AC waveform maintained its shape, its frequency, but its baseline is just shifted up or down by that DC value that it's writing. This combined voltage is often referred to as a pulsating DC, especially in rectified power supplies, where the signal isn't flat, but it's also not fully alternating. This is the kind of waveform you'd see coming out of a function generator with a DC offset applied, a half-wave rectifier before filtering, an amplifier output biased with a DC voltage. It reminds us that in electronics, waveforms are flexible, and we often add or shift them to meet the needs of the specific circuits we're working with or designing. All right, let's go ahead and continue with pulse definitions, pulse basics, where square waves begin. So now that we've covered the elegant curve of the sine wave, let's talk about something sharper, like pulses. Pulses are foundational to digital signals, switching systems, and timing circuits. So instead of continuously varying like a sine wave, a pulse jumps up or down, does it suddenly, and then returns to the baseline, almost like a digital on-off signal. So on this slide, we see two types of ideal pulses. I say ideal, I'll describe why I'm saying that now later. All right, so positive going pulses, which you see on the left side, the waveform starts at the baseline. The leading edge rises sharply to a defined amplitude. It holds that level for a fixed pulse width. Then the trailing edge falls back down. This is typically, typical, of a digital logic signal, like a binary 1 or a clock pulse. The negative going pulse, which you see on the right, here the signal drops below the baseline, the leading edge falls downward, it holds low for some duration, then the trailing edge rises back to the original level. And this kind of pulse appears in inverted logic or as part of differential signaling schemes. And the key terms to know here are the amplitude, which is the height of the pulse from the baseline, the leading edge, which is the initial transition, whether it's rising or falling. The trailing edge is that return to that transition. The pulse width is the time duration the pulse remains at its high or low level. These definitions form the vocabulary of waveform timing, especially when we look at pulse trains, duty cycles, and modulation. Right, continuing on with real world pulses, right? No such thing as a perfect edge. I'll explain this after this slide. So earlier we looked at ideal pulses and those perfect, crisp, rectangular waveforms. But in real life, signals are never that clean. And this slide introduces what's called a non-ideal pulse. And this shows us how to measure them accurately. So in diagram A, we see rise time, T sub R, and fall time, which is T sub F. So when a signal changes from low to high, or vice versa, it doesn't happen instantaneously, right? It's not instant. The waveform ramps up or down. And so we define the rise time as the time it takes to go from 10% of the peak waveform to 90% of that full amplitude peak waveform. Fall time is kind of the reverse, the time it takes to drop or fall from 90% down to 10%. So why not 0 to 100? Because that part of the curve is where things are nonlinear and noisy. So we standardize on 10 and 90% for consistency and accuracy. In diagram B, we look at pulse width, T sub W. And here the width is measured at 50% of the amplitude, not at the top or the base. This gives us a precise, repeatable way to determine how long the pulse is on. So if we summarize this for real world measurements, I gotta say that correctly, real world measurements, right? We have the rise fall time from 10% to 90% or vice versa. The pulse width, which we measure at 50% amplitude level. And these definitions are crucial when you're looking at analyzing high-speed digital signals, measuring timing performance in circuits, and designing edge-sensitive logic systems. So understanding how edges behave lets us anticipate and fix issues with timing, ringing, overshoot, and distortion. Now I said I was going to give you a little bit more at the end of this slide. So the reason we have to look at that ramp up from when it goes from 0 to its maximum, and we measure it from 10% of that lower value to 90% of that value, is because let's say this is voltage or current. And the previous slide, you saw that perfect straight line going straight up at that particular time. That doesn't work in classical physics, right? 2 points, for example, an electron can't occupy 2 different points in time, right? That's something that you would work with in quantum physics and maybe quantum engineering or something if that was possible. So it does take some amount of time for that, whatever you're going to measure, whether it's a voltage or current, to go from some value to the next value. And that ramp, that line that goes sort of at an angle like a pyramid, that represents the fact that our waveform isn't a perfect square wave that goes straight up. That would indicate that something is existing at 2 different points in the same moment of time. That's impossible in classical physics. Not every wave is a sine. Meet the triangle and the sawtooth. Right? So far, we've explored sine waves, pulses, and phasors, but not all waveforms are smooth or binary. Some are shaped by linear ramps. Enter the triangular and sawtooth waveform, or as I like to say now, the triangular. That doesn't sound right. Anyway, these are common in timing circuits, signal generators, oscilloscopes, especially when you need precise, repeatable ramp behavior. Triangular waveforms are characterized by this linear rise and linear fall. The slopes of the rising and falling edges are equal and opposite. This symmetry makes them useful for modulation, control signals, and certain analog audio applications. Think of the triangle wave as a steady climb up and a down on a mountain. A mountain is perfectly symmetrical, going up at a certain angle, coming back down at a certain angle. So equal effort in both directions, no matter which side you go up. The sawtooth waveform is also made up of two linear ramps, but one is much steeper than the other. So typically there's a slow rise followed by a sharp drop, or vice versa, right? So the shape mimics the teeth of a saw, if you know what the teeth of a saw looks like. A wooden, like a saw when you're cutting wood. That's where it gets its name. The sawtooth waves are heavily used in sweep generators, analog TVs, and CRTs, those OTVs. Phase lock loop systems, because they change steadily in one direction and reset quickly. They're great for frequency control and scanning systems. Let's move into harmonics, the hidden frequencies inside every wave. So you've seen that sine waves are smooth and pure, but what about square waves or triangle waves? Again, this is the one. Triangle waves are triangle. I can't mispronounce it. Triangle waves. I forgot how I mispronounced it before. And sawtooth waves, right? So they're more complex, and why is that? They're made up of sine waves stacked together at different frequencies. So these building blocks are called harmonics. The base frequency of a waveform, the rate at which it repeats, is called the fundamental frequency. This is the tone that you hear, or the signal your circuit responds to. But now when we enter harmonics, we have odd harmonics and even harmonics. Odd harmonics, these are the sine waves at 3 times, 5 times, 7 times that fundamental frequency. So square waves, for example, contain only odd harmonics. Even harmonics are like 2 times or 4 times or 6 times that fundamental frequency. These are found in asymmetrical waveforms like certain sawtooth signals. So when we say a waveform is non-sinusoidal, what we really mean is that it's made up of a fundamental sine wave plus a bunch of harmonics riding on top. And the presence of these harmonics determines the shape of the waveform, the sound quality, if it's audio, and the frequency content in filtering and signal processing. So let's start with the building of a square wave, one harmonic at a time. What happens when you add sine waves together? Right? You shape new waveforms, and one of the best examples of this is the square wave. And here in this slide, we break it down beautifully. So a square wave isn't just a blocky signal pulled out of thin air. It's actually built from the fundamental sine wave and a series of odd harmonics. Let me walk you through this. So you see in panel A, that shows the fundamental, the solid black, plus the third harmonic, which is that dashed. So when you add them together, you end up with that blue signal. You get a waveform that starts to flatten at the top and the bottom. In panel B, you add the fifth harmonic to this, or into that whole mix, and now the corners start sharpening and the overall shape becomes even squarer. You move one step further, like in panel C, where you're adding the seventh harmonic, right? And what does that result in? A waveform that closely resembles an ideal square wave, with flat tops and steep transitions, though you'll notice a little ripple, right, on top of each harmonic. So they have a frequency that is an odd multiple of the fundamental, 3 times the frequency, 5 times the frequency, 7 times the frequency. It has specific amplitude and phase, adds detail and edge definition to the final shape, and this whole process is called Fourier synthesis, reconstructing complex signals from simpler sine waves. Continuing on, let's look at two views of one signal in the time and frequency domain. So up until now, we've been building waveforms using harmonics, stacking sine waves of different frequencies, but now it's time to switch perspectives. So what if instead of seeing the waveform over time, you viewed its frequency ingredients? That's exactly what's in this slide. You have a powerful comparison between the time domain and the frequency domain. So let's look at the time domain view. This is a familiar plot, amplitude versus time. You see the waveform as it unfolds in real time. And so for the square wave here, we see ripples from the added harmonics. And we call that the Gibbs phenomenon. This is where the magic of harmonics becomes clear. Each vertical line represents a component frequency. You see the fundamental and then the third harmonic and the fifth harmonic and so on, and their amplitudes shrink as you go higher in frequency. It's like hearing a musical chord. The fundamental gives you the root note, the harmonics give you richness, edge, and texture. And this 3D model shows the waveform shape that it depends on the sum of the harmonics. The frequency domain reveals what's inside, and the hidden structure of the signal is also illustrated there, right? And so why is that important? Because again, in electrical engineering or electronic engineering, time domain helps you diagnose signal shape, delays, and distortions. Frequency domain lets you analyze filtering, bandwidth, interference, and spectrum use. So together they provide a complete picture of signal behavior. Okay, let's go ahead and talk about oscilloscopes. And we're going to break down this particular oscilloscope. If you're in your lab, try to follow along with the actual oscilloscope you have in your lab. So if you're going to work with waveforms, you need to see them. That's where the oscilloscope comes in. That's your window into the signal. An oscilloscope is made up of four main sections, and this diagram shows you how they work together. So we have number one, the vertical section. This is where the incoming signal is first processed. It includes things like signal coupling switches to select AC, DC, or ground coupling, amplifiers that adjust the signal size, volts per division control. You'll see that control there. For digital scopes, a conversion stage stores the processes and the signals, right? So each channel that you see, like channel 1, channel 2, it has its own vertical path, and it allows you to view multiple waveforms simultaneously or simultaneously, depending if you're from the US or here. And so the horizontal section here, this controls how the waveform is drawn across the screen. So the time base defines how quickly the trace moves in seconds per division. It also manages horizontal positioning. So on digital scopes, this section is handled by processing and control circuits. This section turns time into a horizontal axis. It lets you analyze wave shape, timing, frequency, and so forth. The next is the trigger section, and this is the oscilloscope's timing brain. It determines when to start drawing the waveform. It can trigger from channel 1 or channel 2 or some other external trigger, right? External signal. The trigger from channel 1, channel 2, or an external signal, it ensures you see a stable, repeatable waveform, not something that's random in motion. Right? Triggers control can include things like coupling, whether it's AC or DC coupling, and ground coupling, which you'll have in your scope. Level and slope selectors, where you're looking for fine-tuned synchronization. That depends on the display section. So this is the screen, whether it's a CRT or an LCD. The display section shows the waveform's amplitude, which is the vertical, the time progression, which is the horizontal axis, and signal behavior in real time. Analog scopes use a glowing trace, while digital scopes reconstruct the waveform from stored data. So let's get hands-on with the front panel of the oscilloscope. So you see here the oscilloscope's internal structure. And let's go ahead and take a better look at this, the front panel. And this is where the magic happens, where you take control of the signal you're observing. We can take a guided tour across the scope interface. We can look at the vertical section, that left center, and this section controls each input channel. So channel 1 and channel 2, or so if you have more channels than that on your actual scope. Each channel has the following: a position knob, and that moves the waveform up and down on the screen. A volts per division knob, that adjusts the vertical scale, how much voltage each vertical division represents. You have a coupling selector, AC coupling, DC coupling, or ground. AC, when you're in that mode, it blocks DC to show only the changes. DC passes the full waveform, so it'll pass the DC and the AC, and it'll show an AC waveform riding on top of a DC. Okay. The ground disconnects the signal to establish a zero baseline. And so you also have a selector to view channel 1 or channel 2, and 3 and 4 if your scope has more. Or, for example, channels 1 and 2 together. This is useful for comparing signals. In the horizontal section, in that middle section, the position control moves the waveform left or right, and the seconds per division knob sets the time base and how fast the trace moves across the screen. So a setting of 5 microseconds means each division represents 5 microseconds of time. And this is your time axis control. It lets you zoom in or out on the waveform timing. So trigger section to the far right, that trigger area stabilizes the waveform. So key controls like the slope, positive or negative, determines if the waveform starts on a rising or falling edge. The level sets the voltage threshold for the trigger. The source, it helps you choose which channel or external input to use for triggering. And then the coupling, AC-DC, that filters out the trigger input signal. What else? Yeah, so if you have a proper trigger, locks the waveform in place, that makes it readable and consistent. Inputs and probe connections at the bottom, those connect the probes to channel 1, channel 2, or some external trigger. And the use of the probe compensation port to calibrate your specific probes is visible there, ensuring accurate readings. Let's move on to the vertical section where your voltage command center is. Taking a closer look at one of the most important parts of the oscilloscope, the vertical section, this is where you control and interpret amplitude, the voltage part of your waveform. So each channel, let's say 1 and 2, has its own dedicated control, so you can work with single or dual waveforms at once. Here's what each control does. The volts per division knob, this sets the vertical scale. So for example, if set to 5 volts per division, each grid division on the screen equals 5 volts. Turn it to 2 millivolts per division, and you're now analyzing millivolt level signals. Adjusting this is like zooming in or out on voltage. The position knob, this moves the waveform up and down on the screen. It doesn't affect the signal. It just shifts your viewing window, which is great for comparing two signals or centering your trace. Then let's move on to the coupling switch, the AC, DC, and ground. AC coupling blocks DC component and shows only the AC part of the waveform. Perfect for audio or ripple measurements, right? DC coupling shows the entire waveform, including that DC offset. And then we have ground, of course, disconnects the signal entirely and sets a flat line at the ground reference. So this is helpful for zeroing out the vertical position. When you're working with waveforms, this selection will allow you to adjust visibility, analyze voltage levels, eliminate unwanted offsets, and focus on what matters inside the signal. Let us talk about the time control, or the horizontal section. Students forget about this one when they get into lab. So you've already seen how the vertical section controls voltage, so let's focus on time. And that's the role of the horizontal section of the oscilloscope. This section determines how the waveform is stretched or compressed horizontally. That's how much time is displayed across the screen. Let's go ahead and break that down a little further. You have a knob that says seconds per division control, right? It's a time-based knob. This sets the horizontal scale measured in seconds per division. So for example, if I were to set the scope to 5 milliseconds per division, each horizontal grid box equals 5 milliseconds. If you turn it into 5 nanoseconds per division, you're zooming in to nanosecond level events, and changing this setting allows you to um, view an entire slow moving waveform, to zoom in to analyze high-speed transient or glitches. And it's how you match the display to the speed of your signal. So horizontal position knob, this lets you shift a waveform from left to right, adjusting where the trigger point lands or aligning multiple waveforms for comparison. What else? Yeah, this is especially useful when you want to compare signals from different channels, capturing specific segments of a repeating waveform, and analyzing the pre-trigger or post-trigger behavior in single shot captures. So from here on out, you've got the volts per division for vertical, which is the amplitude, seconds per division, which is horizontal for time, and these are two axes of every signal and every signal that you analyze. So you have to master both so that you can bring signals to life on the screen. Okay, locking it in, the trigger section. So you've seen how to scale voltage and you've seen how to stretch time on the scope. But if your waveform won't stay still on the screen, what's the fix? And you'll find that out pretty quickly. Your signal won't, or your waveform won't stay on the screen. That's where the trigger section of the oscilloscope comes in. The trigger synchronizes the signal so that each cycle starts at the same point. And that allows you to get a stable, repeatable display. And let's go ahead and walk through the controls. So first you have the trigger slope, which is plus and minus. And this tells the scope to trigger on a rising edge or falling edge of the waveform. So using rising edge when you want to capture signals going up, and falling edge for events that drop down. The trigger level, this sets the voltage threshold at which the oscilloscope triggers. So for example, you might tell the scope, only trigger when the signal crosses 2 volts going up. And you can fine tune this to capture signal transitions. What else? The trigger source, channel 1, channel 2, or some external line. This tells the oscilloscope which signal to watch for the trigger. So channel 1 and channel 2, they use the waveform from one of the input channels. The EXT, or external, this is used as an external signal as a timing reference. And then line syncs to the AC main signal. So handy for power analysis. Quite a bit. Okay, I think we're almost done here. The trigger coupling, right? The AC and DC. This controls what part of the signal is used for triggering. So AC coupling filters out DC offset and focuses on signal transitions. DC coupling uses entire waveforms, including those DC components. And this is useful for rejecting noise or zeroing in on waveforms. All right, let's go ahead and conclude this. So from signal to screen, the display section. So we reached the part of the oscilloscope that brings it all together, the display. And this is a window where all of your hard work pays off. The waveform you've configured, scaled, and triggered, that's now visible and measurable. So let's explore what's on the screen. The grid itself, we call it a graticule. It's an older term, but it's what it's called. The screen is covered with a grid made of vertical and horizontal lines. You have vertical divisions that show amplitude, like voltage, as set by the volts per division knob. You have horizontal divisions that show time, as set by the seconds per division knob. So each small box is a measurement unit, turning the screen into a graphing calculator for waveforms. The intensity control, this adjusts the brightness of the waveform. So on analog scopes, the controls for the electron beam strength are here. On digital scopes, it adjusts how vivid the trace appears. So if you turn it up to see faint signals, or you turn it down to avoid burning in bright images, especially on older CRT displays, that's where you would use that. So what do you actually see? The display gives you immediate access to the key waveform traits, the amplitude, the frequency and period, the rise and fall times, the DC offset, and signal distortion, noise, or glitches. So whether you're capturing a digital pulse or some noisy AC line or a clean sine wave, the display shows you everything in real time. Okay, as usual, I'm just going to go ahead and go through the terminology that we covered in this section and maybe some that we missed. So the sine wave, a type of waveform that follows a cyclic sinusoidal pattern defined by the formula y is equal to a sine theta, or y is the amplitude, I'm sorry, where a is the amplitude and y is the value of the sine wave at a particular moment. Alternating current, current that reverses direction in response to a change in source voltage polarity. The period, denoted by the letter T, the time interval for one complete cycle of a periodic waveform. The frequency, noted by the symbol F, a measure of the rate of change of a periodic function, the number of cycles completed in 1 second. The hertz, not the car, but the frequency. The unit of frequency, 1 hertz equals 1 cycle per second. Continuing with definitions, we have instantaneous value. This is the voltage or current value of a waveform at a given instant in time. We also have the peak value, the voltage or current waveform, the voltage or current value of a waveform at its maximum positive or negative points. The peak-to-peak value, the voltage or current value of a waveform measured from its minimum to its maximum points. And then you have the RMS value, the value of a sinusoidal voltage that indicates its Heaton effect. So it's also known as the effective value. It is equal to 0.707 times the peak value. And then RMS just stands for root mean squared. Almost done with the key terms. All right, continuing here, radian, a unit of angular measurement. So there are 2 pi radians in one complete 360-degree revolution. A phasor, a representation of a sine wave in terms of its magnitude or its amplitude, and a direction, which is the phase angle. Now, amplitude, the maximum value of a voltage or current measured from the mean for a sine wave. A pulse, a type of waveform that consists of 2 equal and opposite steps in voltage or current separated by some time interval. Harmonics, the frequencies contained in a composite waveform, which are integer multiples of the pulse repetition frequency. All right, as usual, I'm going to ask the questions for the quiz, read the responses. I'll pause a little bit. You can stop the recording to give you more time to think about the question and then turn the recording back on to answer, and then see if your answers match what's in the back of the book. All right, question number 1. In North America, the frequency of AC utility voltage is 60 Hertz. That means the period is what? 8.3 milliseconds, 16.7 milliseconds, 60 milliseconds, or 60 seconds. Go ahead and pause. All right, go ahead and come back. And not that you could hear me, but if you pause and you click to turn it back on, you would have heard and come back. All right, so the answer here is B, 16.7 milliseconds. Question 2, the amplitude of a sine wave is measured in what? At the maximum point, between the minimum and maximum points, at the midpoint, anywhere on the wave. Go ahead and pause. And you're back. Okay, so the correct answer here was A, at the maximum point. Question 3, an example of an equation for a waveform that lags the reference is, and I'm going to just read the letters instead of all those equations. Is it A, B, C, or D? Go ahead and pause. And you're back. And the answer for number 3 is C. V is equal to 5.0 volts times sine of theta, theta minus 27 degrees. Question 4. In the equation V is equal to V sub P times sine theta, the letter V stands for the what? A, peak value, B, average value, C, RMS value, or D, instantaneous value. Go ahead and pause. And you're back. Right? The correct answer for number 4 is D, the instantaneous value. Question number 5. The time base of an oscilloscope is determined by the setting of the what? A, vertical controls, B, horizontal controls, C, trigger controls, or D, none of the above. Go ahead and pause it. All right, I'm sure you're back by now. And the answer to this question is B, horizontal controls. Question number 6. A sawtooth waveform has what? A, equal positive and negative going ramps. B, 2 ramps, one much longer than the other. C, 2 equal pulses. Or D, 2 unequal pulses. Go ahead and pause. And you're back. The answer here to number 6 is B, 2 ramps, one much longer than the other. Question number 7. The number of radians in 90 degrees are what? A, pi over 2, B, pi, C, 2 pi over 3, or D, 2 pi. Go ahead and pause. And you're back. Right? The answer for this one is pi over 2, which is A. Question number 8. For the waveforms shown, the same power would be delivered to a load with a DC voltage of A, 21.2 volts, B, 37.8 volts, C, 42.4 volts, and D, 60.0 volts. Go ahead and pause. And you're back. Now, if you're looking at the sine wave there, we see it goes from 0 all the way up to 60 volts in the positive direction. It also deflects down to negative 60. So our voltage peak would be 60. But we're not looking for that. We are looking for the power that would be, the same power would be delivered to a load with a DC voltage. So we're looking for that DC equivalent. And that would be answer C, the 42.4 volts. Question number 9. A square wave consists of what? A, the fundamental and odd harmonics. B, the fundamental and even harmonics. C, the fundamental and all harmonics. Or D, only the fundamental. Go ahead and pause. And you're back. All right, the correct answer for this one is A, the fundamental and odd harmonics. And question number 10, the last question for this presentation. A control on the oscilloscope that is used to set the desired number of cycles of a wave on the display is what? A, volts per division control. B, time per division control. C, trigger level control. Or D, horizontal position control. Go ahead and pause the video now. And you're back. And the correct answer to this one is B, time per division control. Go ahead and compare your answers to the solution here and go through them again until you completely understand why the right answer is the right answer, and also why the wrong answer, if you got something wrong, why it is the wrong answer. And if you can do that, you're good to go. Thank you very much for your time, and I'll see you in the next presentation.